Hello, welcome to a presentation today by Dr. Timothy Lash from Emory University. His topic today is Quantitative Bias Analysis, the Good, the Bad, and the Ugly. This is a first of a planned series of webinars sponsored jointly by the HESI, International Society for Environmental Epidemiology, Quantitative Bias Analysis Special Interest Group, and HESI Global. I have a few slides that I'll go through before Dr. Lash's presentation, which will just introduce you to the two organizations, and then I'll pass it on to Dr. Lash for the rest of the time. Is that okay, Dr. Lash?
I see a nod.
Okay, great, thank you. So next slide, Sandrine, please. Okay, as I said, today's presentation is by Dr. Timothy Lash, and I'll just kind of give a bit of a preview of the next session, which is scheduled for February 5 of next year. It will be by Dr. Igor Burstin from Drexel University. He'll be talking about QBA and recall bias in population-based case control studies of ovarian cancer and genital talc use. On that. That will be related to the recent IARC monograph, and he'll be presenting an approach to that using Bayesian methods on that. We have more sessions planned, which we'll announce later for 2026 until the ISCE annual meeting in Munich. That takes place August 30th through September 2nd. I'm looking to organize as the QBA SIG chair a symposium there. If folks are interested in presenting at that session, please let me know. I have my email at the last slide that we'll present at the end of the presentations on there. So just if folks think they'd like to mention to talk there, that would be great. We're looking for speakers on that. Just a little bit of intro in terms of the ISCE SIG on QBA. I won't go through all of this in detail. Just the goal of it was to promote awareness and uptake of QBA methods in environmental epi by fostering ongoing dialogue, education, shared resources, and community building. It was launched officially by the Executive Committee, a series of SIGs in 2024 to encourage or foster between meeting communications and collaboration around specific specialized topics. It was formed, the QBA SIG was specifically formed in response to a growing interest in addressing systematic error in environmental epidemiology, and it's intended to encourage researchers and practitioners to exchange experiences, address challenges, and share solutions in QBA. Supports ISCE's broader goals of transparency, rigor, and relevance in research. We will be having an ICE QBA SIG website that will be coming probably in the next couple of weeks, where additional information will be provided on that. And you can see the graph to the right just indicates the membership by sector. We have 48 members in the SIG representing 11 countries on that. Next slide, Sandrine, please. Sandrine.
Yep.
Yes. Okay, great. Yeah, the HESI's Global Environmental Epi Committee. The mission of that is to take action to help realize the full potential of epi data in risk assessment and regulatory decision making. It was launched in 2017 with representation by academia, government, and industry, with academia and government co-chairs on that. It emerged from the belief that epi evidence can play a greater role in human health risk assessment. It's organized. One of the things that was done is organized a webinar series. The link is there that highlights critical role that epi can play in quantitative risk assessment and showcases ongoing efforts in this space. Published various articles on better integrating epi into risk assessment and public health decision making. And you can see the website is there if you're interested on that. And we'll post them. Just one of the activities began a couple of years back of the HESI Global is the QBA initiative on QBA activities. The goal was to increase the understanding of QBA and popularize its use, making it more accessible to users lacking the necessary coding and statistical skills. A number of milestones there. I won't read through them. We expect an educational manuscript to be published later this year that highlights the method on that. Next slide, Sandrine. Just in terms of today's webinar, just a little bit of the logistics. The webinar is being recorded, and folks will be able to access it afterwards. It'll be posted on the Environmental Epi Committee webpage of the HESI Global website. We're also looking to get it posted, maybe by a link to the forthcoming SIG QBA SIG website on that. We ask that you remain muted at all times during this session. Please use chat to type in your questions. We'll read them at the end. If you have questions about the ISEA QBA SIG, you can contact me. My email's there. And if about the HESI project, you can contact Sandrine, and her email is there. Those emails are also repeated on the last slide that we'll show at the end of Dr. Lash's presentation. So with that, I'll just kind of give a quick intro before turning it over to Dr. Lash. I'm delighted to introduce him. He is the chair of the epidemiology department at Emory University's Rollins School of Public Health. He's been a leading voice in making quantitative bias analysis accessible and practical for applied epidemiology, helping researchers better understand and address systematic error in observational studies. His research focuses on cancer epidemiology and methodological innovation, and he serves as editor-in-chief of the journal Epidemiology. He's also author of 2 cornerstone textbooks, Modern Epidemiology and Applying Quantitative Bias Analysis to Epidemiological Research on that. With that background, I'm delighted to turn it over to Dr. Lash to guide us through the good, the bad, and the ugly of QBA. Dr. Lash.
Thank you, David and Sandrine, and thank you for having me, and also to your respective organizations for arranging this webinar. So I am going to talk today about quantitative bias analysis, and it's useful, I think, to start with a common premise, and this is my description of the objective of epidemiologic research, which is to obtain a valid, precise, and generalizable or transportable measure of the occurrence of disease, if we're talking about descriptive epidemiology, or the effect of an exposure on the occurrence of disease, if we're talking about etiologic epidemiology. And so the parts of this objective that I want to really highlight are, first of all, that this is, in my view, an exercise in measurement, not testing. And that the measures that we seek to obtain have characteristics. They should be valid, meaning lacking systematic error, precise, meaning lacking random error, and then useful, meaning we can bring them from our research and apply them elsewhere to improve public health. So if that's the objective, then the premise of my talk is that since this is an exercise in measurement, we have an obligation to quantify how far from that objective we might have fallen. In other words, all measurements have error. What are the sizes of the errors in the measurements that we make? Now, conventionally, we quantify how far from the mark we might have fallen due to chance, sometimes in concert with testing, rather than estimation. So things like confidence intervals, p-values, likelihood ratios, all of these quantify the random error in our measurement. If you read the definitions of them, they ordinarily require an assumption of no bias, in other words, no systematic error acting on the adjusted estimate. We don't conventionally quantify our uncertainty due to systematic errors, even though those errors oftentimes dominate the uncertainty. And that's especially growing true as data has become more abundant in this era of big data. Random error is actually often quite small, and the uncertainty is dominated by systematic error, but our conventional approach has not been to quantify that. So what's good about quantitative bias analysis is that it does that. It quantifies the uncertainty due to systematic error. And in my lexicon, by quantitative bias analysis, I mean all of the methods that adjust a conventional estimate to account for the bias and uncertainty arising from systematic errors. So some of the methods I'll show or talk about, but also missing data imputation, empirical direct bias adjustment, regression calibration, all of this falls under the umbrella of quantitative bias analysis. So it's helpful to have some understanding of our terminology, which I'll illustrate using a simple selection bias problem. So let's imagine a cohort study of 1,000 people with the true data shown in the upper left-hand corner, 100 of 500 exposed persons diseased and 100 of 500 unexposed persons diseased. So the odds ratio would be 1 and the variance would be 0.025. And so that's the, the ideal study if we could include everyone. But let's imagine that not everybody participates. So the participation proportions are shown in the 2x2 table in the lower left-hand corner, and they differ by disease status and exposure status. So what we expect to observe would be the table in the top right-hand corner. And you see that the estimate that we obtain from that table, which would be the conventional estimate, is not null. It's 1.3. And it has a larger variance because we have a smaller study size. And so, that's the problem, that the estimate that we get, the conventional one that we would ordinarily have available to us, is different from the truth. And that difference doesn't come from chance, it comes from a systematic error. That systematic error is the difference in selection proportions. Now, we can bias adjust for that with a bias model. So the bias model is just the set of equations that relate the observed estimate, here with the caret over it, to the true estimate as a function of some bias. And in this case, that bias is just a function of the selection proportions. So the 4 selection proportions are the bias parameters of the bias model. And if we fill in the selection proportions and with a little algebraic rearrangement, we get a bias adjusted estimate that's equal to the true estimate. And so that is the beauty of quantitative bias analysis, is that you expect to get an answer closer to the truth upon bias adjustment. Now, the problem is, what values do we assign to the bias parameters? So here in this little toy example that I've given you, I made up the selection proportions, the 70%, 60%, 40%, 45%. And so we know it. But in reality, what we might know is just the marginal participation proportion. So for example, we would know, let's say that we invited 200 cases to participate and that only 130 of them did. So we would know the marginal participation rate of 65%. But for the 70 non-participants, we wouldn't know their exposure status. We would need them to participate in the study in order to learn their exposure status. That's why we're doing the study. And so we would not know the interior participation rates of 70% and 60%, just the marginal participation rate of 65%. And so assigning values to the bias parameters is always the hard part about quantitative bias analysis. We'll never know what values to assign with certainty. And it is that uncertainty in the assignment of the values that gives rise to the additional uncertainty arising from the systematic errors. So how do we find values to assign to the bias parameters, such as these selection proportions? Well, first of all, as I just said, they're not identifiable. There's never going to be data that allows you to estimate them with certainty. Sometimes you might have an internal validation sub-study, as in the example that I'll show in a minute. Sometimes there might be external data to suggest what values should be assigned. Sometimes we're left just making an educated guess. What is inevitable is that we should usually not just assign the implicit values of no selection, right? I mean, that we know is wrong. So if we just treat the conventional estimate of 1.3 as if it was observed without selection, we know that's wrong, right? Because even though we don't know the 70% and 60%, we know that only 65% of cases participated. So we know for sure that there is some source of uncertainty that we're not accounting for if we just ignore the selection. So the example that we're going to look at is an exposure misclassification problem, and it has similar kind of form. We have like a true table on the left with capital A, B, C, and D as the true frequencies of exposure and disease. And then we have an observation, which is shown with lowercase a, b, c, and d. And it's a function of the true frequencies and the sensitivities and specificities. So what we expect to observe is a function of sensitivity and specificity. But of course, we wouldn't start with a true table and go to the observation. We would start with an observed table and want to go backwards to the bias adjusted estimate. And so that's just an algebraic rearrangement. And so the equations on the right-hand side under the bias adjusted table, those are the bias models for an exposure misclassification problem. So given the observation and estimates of the sensitivities and specificities, we recalculate what we expect would have been the true or better estimate. And we can get these estimates of sensitivity and specificity from external sources, from literature, from pilot studies, from sub-studies with gold standard measurement, to inform the values that we assign to the sensitivity and specificity. Now, I want to make the point that what really matters in most exposure misclassification problems is the specificity. And, that's important because we have these two words that are the metrics of exposure classification, sensitivity and specificity. They sound the same. They both start with S, have the same number of letters. Like these seem like they're equivalent words, but the fact is when the exposure is rare, the strength of bias is driven by the specificity. And so here's just my cartoon to illustrate that. Let's say we have a case where the exposure prevalence is 10%, and that's represented by the blue bar on the left. And the unexposed prevalence then is 90%, the remainder, and that's represented by the red bar. And the risk in the exposed is twice the risk in the unexposed. So the risk difference is 0.02 minus 0.01 is 0.01. So that's the true data. Now let's imagine that we have a problem of exposure misclassification where we only find 10% of the exposed. So the sensitivity is 90%. What happens is that blue bar's width gets reduced by 10% of it. So 10% of 10% is 1%. And that blue bar gets mixed with the red bar as people misclassify it as unexposed when they are truly exposed. And so the risk in the exposed group doesn't change. It's just measured in a smaller sample. 9% of the population instead of 10% of the population. But the risk in the unexposed group, now shown in purple, is a mixture of the risk in the true risk in the unexposed, measured in this huge swath of red, mixed with this narrow bar of blue. And so what you see is that the true risk, which was 0.01, is biased upwards towards the risk in the exposed group, but only a small amount. 0.0101 is the risk that we would expect to observe in the unexposed group. So the risk difference, which in truth is 0.01, is hardly biased by this misclassification. Now, if we change this to 100% sensitivity, but 90% specificity, things are actually quite different because now The risk in the unexposed group is measured without bias because there's no mixing in the unexposed group. But 10% of the 90% who are unexposed, which is 9% of the total population, gets mixed with the 10% who are truly exposed. And so you almost have now 1-to-1 signal to noise in the exposed group. And so we end up with a much larger problem because the risk in the exposed group is now a mixture of about 50-50 true risk and incorrect risk. And so the risk in the exposed group that we expect to observe should be 0.02. It's actually 0.0153 that we expect to observe. And now the risk difference is cut almost in half. And so you get a very strong bias towards the null from this misclassification. So a 10% misclassification in both cases, but the specificity has a much larger impact on the strength of bias. And that's true also if we misclassify both have both imperfect sensitivity and imperfect specificity. So the main takeaway is when the exposure is rare, strength of bias is driven by specificity. Similarly, if you have a disease misclassification problem and the disease is rare, strength of bias is driven by specificity of the disease measurement. Now, the bad, as I kind of alluded to earlier, is we'll never know the values to assign to the parameters of the bias model with certainty. Like, we're just never going to know that. And I'm going to show what's, kind of what the consequences can be using an example, which is, I'm sorry, it's not an environmental epidemiology problem, it's a pharmacoepidemiology problem. And this was a retrospective case control study of the association between use of antidepressants and breast cancer risk. It's published in 2006. It's a population-based case control study where the cases were women 65 and older in Western Washington in the United States, diagnosed with breast cancer 1997 to 1999 and reported to the SEER Cancer Registry. Controls were from healthcare records. Medicare is the public health insurance for people 65 and older in the United States. And so it kind of acts like a census of people 65 and older. And so controls were sampled from those records, matched to cases on age, calendar year of diagnosis, and then county of residence. And both cases and controls were asked about a number of different risk factors for breast cancer, including their 20-year history of using antidepressants by an in-person interview. So this is a retrospective design. Cases have already been diagnosed with breast cancer, and that diagnosis might affect their accuracy of recalling or reporting their medical history, behaviors, including use of antidepressants. Controls wouldn't have that same kind of memory stimulus. That's classic recall bias problem in epidemiology. Now, the result was an odds ratio of 1.2 with confidence interval 0.9 to 1.6. And the interpretation of that estimate written by the authors was that there was no association between ever use of antidepressants and breast cancer risk. Here's their 2x2 data. And I'm showing you it for a couple of reasons. First of all, to point out that the antidepressant use was rare. Of the almost 1,000 controls, about 10% had used antidepressants in the previous 20 years by self-report. And the crude odds ratio just from the 2x2 table almost exactly equals the adjusted that was reported in the paper. So that implies we don't need to worry about confounding or adjustment for other confounders or adjustment for the matched factors. The 2x2 data are sufficient to provide a decent estimate of the adjusted estimate. So we can just work with these 2x2 data. And the question is, could this null result be due to misclassification of self-reported antidepressant use? So you can imagine that there may be errors in recalling or reporting 20-year history of antidepressant use. And so that might have created a bias towards the null, which could explain all or part of this point estimate being what the authors interpreted as a null result. Now, to their credit, the authors knew that, and so they did a validation sub-study. And that was separately reported in a paper by Boudreau et al. In 2004. And because of the retrospective design, they used validation data stratified by case and control status. Now, they didn't have 20 years of electronic pharmacy records to use as the gold standard. They had different look-back periods. The one that we're going to be focused on is a 2-year look-back period. And here in cases, you see that of the 43 cases whose pharmacy records show that they had been prescribed an antidepressant, 24 of the 43 had reported on the interview. So that's a sensitivity of 56%, which might map to our prior what to expect. Unfortunately, use of antidepressants might be a stigmatized exposure, so you may get incomplete reporting of that history by self-report. On the other hand, of the 146 breast cancer cases with no electronic pharmacy record of an antidepressant prescription, 144 reported that they had no prescription. So the specificity is 99%. And again, this might map to what you would expect, that people with no history of antidepressant prescription would be unlikely to report that they had such a prescription in the interview. So these are for the cases. And we got very similar validation data in the controls. Sensitivity was 56% in cases, it's 58% in controls. Specificity was 99% in cases, it's 97% in controls. So, although we might have been worried about recall bias, it appears that the point estimates of sensitivity and specificity are not that different between cases and controls. So as a preliminary kind of bias adjustment, we could just take the midpoint, say sensitivity of 57%, specificity of 98%, do the bias adjustment using the bias model that I showed you earlier, and we get a bias adjusted estimate of 1.3. That's further from the null than the 1.2, which is what you would expect, given that this bias model assumes non-differential misclassification. In other words, the same misclassification, sensitivity, and specificity in cases and controls. And that's going to be universally true. This is what we call multidimensional bias adjustment, where we subject the bias analysis to a sensitivity analysis, assign different values to these sensitivities and specificities in different combinations. And so here we've chosen sensitivities of 0.5 and 0.6, kind of right in the range of the observed sensitivities, 56 and 58%. And then specificities of 1 and 0.95. And then this is all possible combinations of those sensitivities and specificities. And you see that the descending diagonal, those are the non-differential scenarios, are all further from the null than the original estimate of 1.2. Similarly, we can see that, as I pointed out earlier, the strength of bias really depends on the specificity. So, if we set specificity to be perfect, 1, and sensitivity 0.6, we get a bias adjusted estimate of 1.24. But if we hold the sensitivity fixed at 0.6 and change the specificity to 0.95, you get a much larger bias from the null, all the way from 1.2 to 1.42. So that's a much stronger bias adjustment, and that comes from changing the value assigned to the specificity from 1 to 0.95. And then the last thing we can kind of see in this table is that if this is a reasonable range of uncertainties for the sensitivities and specificities, the uncertainty due to exposure classification is much larger than the uncertainty due to chance. The 95% confidence interval was 0.92 to 1.61, and the range in this table is wider than that, 0.86 to 1.98. Now, this kind of tabular sensitivity analysis of the bias analysis is nice, but kind of takes a lot of room to go through all of these scenarios. A bigger problem is that we don't really get any sense from that table of which of the point estimates are like what's the central tendency, which one is somehow best. And even though there's a range in the table, that's not really the same as a 95% confidence interval, right? Those are just the extremes within this table, but we don't know where they are in some kind of frequency distribution. And so the solution to that is what we call probabilistic bias analysis. So then rather than assigning one bias parameter set at a time, like sensitivity of 57%, specificity of 98%, or sets of values to the bias parameters, like in the multidimensional table, let's just assign a distribution to the sensitivities and specificities, sample from those distributions repeatedly. With each sample, calculate the bias adjustment using the bias model, and then accumulate the results to generate a frequency distribution. We can get then a central tendency from that, like the median of the estimates, and also an interval equivalent to the 90%, 5% confidence interval. And there are methods to even simultaneously incorporate random error so that we have total error represented in the interval. So the goal here is to use Monte Carlo simulation. That's basically what we're describing here, to get a bias adjusted estimate and its interval. Now there are lots of tools that do this now. There are Matfox is published on our textbooks webpage, Excel spreadsheets that do it. There's R code that does it, there's data code that does it, there's SAS code that does it. Some of it we've written, some of it we link out to others who have written there's a Shiny app that does it. So we, kind of check the validity of the method. Once we are sure that it works, we link out to it. So you can find lots of different tools that do probabilistic bias analysis for lots of different biases, including these kind of exposure misclassification problems. Here I've just used this simple spreadsheet that Matfox makes available. And if we take the 2x2 data as observed, and then assign beta distributions to the sensitivity and specificity, we get a bias adjusted result of 1.69 with interval 0.9 to 4.24. Now, unpack this a little bit. First of all, beta distributions are very useful distributions for proportions because they're naturally constrained to the range 0 to 1. And you see here, the red line is the estimate for controls, sensitivity, and is there near the center, and the blue line is for cases. And you see there's quite a lot of overlap in the distributions for the sensitivity and specificity. They look kind of normal. That's partly because they're near the center of the range 0, 1. But they're also wide, and that's because they are informed by only, for example, 43 people in the case of the cases. Now, the specificities, on the other hand, are much narrower distributions, and that's because they're informed by many more people. And they overlap, but not that much. Like, this is starting to look like maybe the specificities are different between cases and controls, which is something that would be allowed by the retrospective design. And so although the I might have said 97% and 99%, those are pretty close to each other, can we just assume 98%? there's actually some evidence that the specificities are different, which becomes important because specificity drives the strength of bias. And if they're different, then we would want to incorporate that difference into the bias model. So that's where things start to get ugly. Like the lack of widespread use of bias analysis combined with this impossibility of perfect values opens the opportunity for errors and even potentially for manipulation. And so if we go back to the Chen et al. Original paper, they had the validation data and they did a bias analysis. Now this was 2006 paper. So before probabilistic bias analysis methods were published. But they said, you know, since we have information on the sensitivities and specificities, we can calculate what they call the true odds ratio. We would say the bias adjusted odds ratio, using the pharmacy records as the gold standards. And they do that, and they say their bias adjusted estimates don't really differ from the conventional estimate of 1.2, and conclude, therefore, the importance of recall bias may be limited. So they used their validation data in combination with bias adjustment as a shield to protect against this threat to validity coming from exposure misclassification. They're saying, dear reader, don't worry, we've done the bias adjustment using an internal validation study, and the exposure misclassification doesn't matter. Now, they go on to cite that Boudreau study of the validation data and give the sensitivities explicitly as 56 and 58% for the 2-year look-back window. There was also a 6-month look-back window and an 8-year look-back window. I can go on if you want to know more about the details of why there were different look-back windows, but the one we're focused on is the 56 and 58%. So those are the values that were assigned to the sensitivities, and they explicitly cite them in the Chen et al. Paper. But when it comes to the specificities, they say that they tended to approach or equal 100%. And they don't give us the specific values that they used for the specificity. And remember, strength of bias here is driven by specificity. You can assign just about any value to the sensitivities. If they're close to each other in cases and controls, it's not going to make that big a difference. But the specificities matter a lot. And if you look at the Boudreau 2004 validation data, here highlighted, there's the sensitivity of 56% in cases and 58% in controls, and the specificity of 99% and 97% that I showed you earlier. So there is not in the table where we find the 56 and 58, specificity is not 100%. It's 99% and 97%. There is in another table, specificities of 100% for the 2-year look-back window. But in that table, the sensitivities are not the 56 and 58 that Chen et al. Told us they used. They were 61% and 54%. So it seems like Chen et al. Mixed sensitivities from one table with specificities from a second table. And that gets you the result that we observed for them, right? They said that their bias adjustment was near the conventional estimate. In the last row, you see if we use 56% and 58% and 100% specificities for both cases and controls, we get a bias adjusted odds ratio of 1.14. But the actual data are from the row above, where 56% and 58% with specificities of 99 and 97, that gets us a bias adjusted odds ratio further from the null all the way up to 1.68. And so it seems like maybe the values assigned to the bias parameters were selected to get a result that provided assurance that misclassification was not important, when in fact it might be. Like, breast cancer's topic area that I work in, an estimate of 1.68 as a causal factor for breast cancer is kind of big. Like, that's the same size as moderate alcohol consumption, and many of the history of reproductive characteristics that are established risk factors for breast cancer, they are about that size. Now, there are other methods to do the bias adjustments. There's a paper from Sandra Greenland in 1988 that allows you to use the validation data exactly as reported and build all of this into a direct bias model. So Matt Fox wrote the spreadsheet that implements the Greenland method. It's on the webpage. You have the observed data in the top left-hand corner. You've seen those frequencies before. Then you can put the validation data in directly here for cases and for controls. And then everything below those tables are intermediate steps in calculating the bias adjustment. And what you get is, first of all, from the 2x2 table, the conventional result and its confidence interval. You've already seen that. Then we get the bias adjusted estimate and an interval that would be the interval that would be calculated directly from the 2x2 bias adjusted table. And its width is only 1.62. That's the ratio of the upper limit to the lower limit, which is actually slightly narrower than the width of the conventional result. But that width ignores the fact that the bias adjustment relies on sensitivities and specificities that themselves have been measured with random error, right? Like, the sensitivity has only been measured in 43 people. So there's binomial error from that has to be carried forward. And that's all of these intermediate calculations that you see on the right-hand side under the validation data. And when we incorporate that in, we get a wider interval, right? And that's Greenland's way of calculating bias adjustment in its interval directly, as opposed to through simulation. So we can subject this all to a sensitivity analysis of the bias analysis. Start with the conventional analysis that had a point estimate of 1.2 with interval 0.92 to 1.61. If we use the Boudreau observed sensitivities and specificities, we get 1.63. The Greenland method also gives 1.63 with a wider interval. And if we carry forward the uncertainty using simulation instead, we also get a wider interval. So any way you do the bias adjustment, if you bring forward the validation data exactly as reported, we get a bias adjusted estimate of close to 1.7 and an interval that is much wider than the conventional estimate. And so remember what Chien et al. Concluded. There were kind of two conclusions in their paper. First was that there was no association between every use of antidepressants and breast cancer risk. And second, the importance of recall bias may be limited. I think that this bias adjustment is counter to both of those conclusions. The estimate of about 1.7 is not what I would interpret as no association between every use of antidepressants and breast cancer risk. As I said, that is a pretty strong risk factor for breast cancer. And it's quite different from their conventional estimate of 1.2 and their bias adjusted estimate of 1.2, which did not use the validation data as reported. And so their second conclusion, the importance of recall bias may be limited, that emanates from what appears to be selective use of the validation data. And using the validation data exactly as reported, to me, suggests that recall bias might be important. Which brings us maybe to the most important point, and one of the great utilities of bias analysis. What this shows to me is that the uncertainty in this study is not coming from random error, it's coming from exposure misclassification. And that tells us that what we need to do next is a better study with better methods for exposure classification. Prospective design so that we don't have an expectation of differential misclassification, recall bias, and ideally with better quality use of antidepressant data, pharmacy records, right? Registry-based research instead of self-report of antidepressant use. Those studies have been done. They're null. So I don't want you to leave today thinking that antidepressant use increases the risk of breast cancer. I think it doesn't. But what you can take from this kind of analysis is that the main source of uncertainty is from uncertainty due to exposure classification errors, and the next study should improve on that. We don't need to repeat another retrospective case control study of this design. It's going to have the same problems. It guides the research agenda, pointing out where the main source of uncertainty is so that you can design a better study to reduce that uncertainty going forward. I think this is an underappreciated utility of bias analysis, is in guiding the research agenda and identifying what the main sources of uncertainty are. So I will end there with thanks to many colleagues who have worked with me on these topics for close to 25 years now. Still have work going on. I'm about to press the button on another large simulation that we've been working on. So with that, I will be happy to take any questions.
Great. Thank you very much, Tim. I think we have a closing slide with Sandrine, if you could put that up. It's got the Great, thank you very much. The addresses and such. Go ahead and type in any questions you have into the chat. I'll go ahead and read them on that. As I said before, recording will be available for a few days on the Environmental Epi Committee page of HESI's global website. I'll remind folks before we get to the questions, the next webinar will be Dr. Igor Burstin in February of next year. And as indicated before, questions about the ISC QBA SIG, you can contact me with my email address there, and the HESI's IP program, you can contact Sandrine on that. I'll actually just start kind of while we're waiting for the questions to come in, Dr. Lash. A question, so if somebody comes and basically says, look, I've done this study, I'd like to do a QBA on it, but I don't really know what the sensitivity and specificity is. I haven't done kind of sub-studies or something like that. Any thoughts back on kind of how would you respond to that?
Yeah, you know, we've been getting that question for 20 years. So
okay.
I'm going to repeat back Carl Phillips' answer on that, which is you have a variable, an exposure that you believe is misclassified, and you have no idea what the sensitivity and specificity are, like absolutely zero idea what they are. What are you publishing? Like, what's your conventional estimate then? Right. So I'd start with that, is like, if you realize that the variable has been misclassified and truly have no sense of how badly it's been misclassified, what's your obligation then to even publish the original result? And so when you press in that way, what you learn quickly is that people actually do have some idea of what the exposure misclassification might have been, right? Because there are other variables like it, and you have some idea, you know, for example, self-report of tobacco use, you know, again, sitting here, I bet we would all think without knowing the data, well, probably you find something less, you know, not everybody who's a current smoker accurately reports that because of the current social norms. And on the other hand, just about everybody who is a not smoker, truly a not smoker, would not report that they are a smoker. Again, just corresponding to social norms. And in fact, that's what you find. You look at the exposure validation data, sensitivity is about 50%, specificities 99, 100%, something like that. So you may not know the values from the kind of validation data that I showed you here, but when pressed, usually you actually do have some idea of what the misclassification might have looked like, and you can incorporate your uncertainty by choosing different distributions or different assumption sets, like the table that I showed you, and it works pretty well. And from that, you might learn, oh, this is an example where the strength of bias is likewise is driven by specificity. Instead of doing another study, what I need to do is a validation study, right? Like that would have real utility to move this evidence base forward, because it's really the uncertainty is driven by misclassification of the exposure, and no one has measured that. And so rather than doing another study without improving our understanding of the misclassification, it'd be better to direct resources to a validation study than to another study that just adds to the same uncertainty.
Great. Thank you very much. So it sounds like QBA is also useful for, I mean, as you say, kind of directing the field on that in terms of doing another study may not add much, basically, unless you take into account some of these things, and it tells you where you need to take those into account. So thank you. So we have some questions come in, so I'll kind of read them. How would one approach data where the exposure is continuous, a measured dose rather than binary, and we want to gauge the influence of a binary unmeasured or incompletely measured confounder, say smoking?
Yeah. So for continuous exposures, regression calibration is the gold standard bias adjustment method, in my view. Donna Spiegelman's work, which began with nutritional epidemiology, continuous intake of nutrients and micronutrients, and then she applied that to air pollution epidemiology, works quite well. And so unless there's something specific to the setting, that's the first place that I would turn, would be regression calibration. And regression calibration is just basically amplifying the estimate to take account of the imperfect correlation between the measurement that we have in everyone on a continuous scale and some gold standard measurement, like air quality measured at a monitor as the measure that we have available for everyone in the study. And then, personal air monitors on a subset, which is very expensive, hard to collect, but gives you the point source that you're interested in. You get the correlation between those two in a subset of the population. That correlation is used to amplify the estimate to account for the non-differential misclassification.
Great. Okay. Thank you. And kind of a quick related question to that that's come up in terms of how ugly that might be. You mentioned the regression calibration. It seems quite clear when exposure is binary, but how ugly might it be when exposure is continuous? As you mentioned, like air pollution, it says what kind of analysis could be applied then? So you answered what kind of analysis. How ugly does that get? Does it?
Not ugly. The tools are out there. Like, Donna's been publishing the code on her website for 20 years. So it is, all of these methods are just algebra. Like there's compared to methods that we've routinely become accustomed to implementing that I think are much more challenging computationally in terms of the statistical code. Bias analysis is just algebra. And it's easy. The challenge is always what values do we assign to the bias parameters.
Okay, thank you. Another question is, when conducting systematic reviews of observational studies, there are some risk of bias tools that assess the risk of bias in the included primary studies. Is there a utility of quantitative bias analysis in oh, I'm sorry, just disappeared. Is there a utility in quantitative QBA in systematic reviews of observational primary studies?
Yeah, great
So-
question. We've just published 2 papers on this very topic showing that in topic areas where there's been some controversy about heterogeneity of the results and lack of reproducibility, that if you apply bias adjustment to the published estimates to account for the major sources of systematic error, you reduce that heterogeneity substantially, and that an evidence base that appeared to be heterogeneous suddenly looks quite reproducible, like, and so it works. It's as you would expect, because you are taking account of the differential strength of bias in the different studies. If you can, on average, eliminate that, things begin to look like they're more like they're just sampled from a random distribution. I'll bet you anything that's what Igor is going to talk about when he talks about ovarian cancer and talc use in February. It works, and it should. Like, so we, as I say, we've just published a paper in CEBP and a paper in American Journal of Epidemiology on this very topic.
Okay, great, thank you. And so it seems like when you're doing, say, a meta-analysis, combining various studies together, the bottom line is if you use QBA on those, you actually might get a kind of more consistent answer because it takes into account some of that heterogeneity.
And just to be clear, like, it's not my idea. Sandra Greenland wrote about that in the meta-analysis chapter in the second edition of Modern Epidemiology before I was an author, that that would be a useful way to do meta-analysis.
Okay, thank you. When incorporating the random error of sensitivity and specificity to calculate confidence intervals for the odds ratios, for example, there seem to be 2 approaches: theoretically based on simulation-based confidence intervals versus or theoretically based versus simulation-based. Any thoughts on strengths and weaknesses on these 2 approaches?
Yeah, so the Greenland method that I showed you, I think, has a couple of theoretical limitations. First of all, when we have used like the beta distributions and simulation method, we usually build in a correlation so that you don't get, for example, in our study, draw a sensitivity for cases of 35% and a sensitivity for controls of 65%. That is probably an unlikely combination. And so by establishing a correlation between the 2 sensitivity distributions, you don't get that kind of wide dispersion. And the strength of that correlation, no one knows, empirically what to set that to. It's been conventionally set to 0.8, but you can evaluate the sensitivity of the analysis to that assumption. The second thing is that the Greenland method, the variance for the sensitivities and specificities rely on large sample approximations, and the size of the validation data that we had from Boudreaux were not really large enough to satisfy that assumption. And so what you end up with is normal distributions that have a substantial part of the density above 1. And of course, you can't have a proportion above 1. So the method works, but there's an underlying problem with it that is hard to spot. And so for those 2 reasons, I prefer the simulation method that we use. Those are both addressable with the Greenland method, but in the paper as written, they're not implemented.
Mm-hmm. Okay, thank you. Another question, a kind of more generic, general one. How should we effectively communicate the results of QBA to the public and to policymakers?
Yeah, great question. So I have not in any circumstance found resistance to the result of a bias adjustment, right? The editors like it, reviewers like it, grant reviewers like it. And I have worked with people in the FDA and EPA who like it also. I have not met anyone who's not interested or who doesn't believe it. So that's 1. 2, I think that the main way to communicate it is describe what was done, what the premise was for why you're worried about the systematic error that we're concerned about. Mostly people get that. Like, you're not gonna have a hard time convincing someone that someone might misremember or misreport their 20-year history of antidepressant use, right? Like, that's not a hard concept to convey. And that that there's methods to adjust for that. And then if you give them the point estimate and the interval, it looks just the same as the conventional results. So there's no more to do there, right? All you've really done is said, you're used to seeing the result in an interval that only takes account of random error. This one takes account of that random error and the uncertainty due to self-report of the antidepressant use. People get it.
Okay.
That's where I think the tables are actually more confusing, right? Like, then you've got 24 point estimates and you have no idea which one to listen to. So I think that whether you do it by simulation or by direct bias modeling like the Greenland method or regression calibration, a point estimate and an interval is digestible. People are used to seeing that. You just tell them this one is a little bit different because it's adjusted for this source of systematic error that I've explained to you and the extra uncertainty from that.
Okay, thank you. Another question, when conducting observational studies, we often face multiple biases simultaneously, say exposure misclassification along with unmeasured confounding. How do you recommend prioritizing or combining bias analyses when it's not feasible to model them all at once?
Yeah, great question. So you can do these bias adjustments in series, and the usual recommendation is to do them in the reverse order that you think they occurred. So most frequently we would think confounding is a fact of nature, if you will. And then you have selection into the population, study population, and then you have measurement error among those who participated. So if you're doing the bias adjustment, you would do it in the reverse order. Bias adjust from measurement error, selection bias, confounding. You can just do it in series. And, we are actually working on a question of whether there's ever cases where that might lead you astray. So far, we haven't found anything that seems like it's a big problem to do them just in series like that.
Okay, thank you. We're getting close to the end of the question. I think you kind of addressed this one before, but I wondered if there's anything you want to add to it. It's the heterogeneity question. Thank you for this excellent talk. In their 2006 paper, they seem to find significant odds ratios in subsets of breast cancer. Since true heterogeneity may also play a role, how does QBA fit into our discussion section?
True heterogeneity, well, by that I assume you mean that there is effect measure modification, right? Like, an exposure may have a particularly strong effect in a susceptible subpopulation. That heterogeneity is real, and you would want to acknowledge it. And the bias adjustment should improve the ability to observe that, right? If you apply it within straight of the effect modifier.
Okay, yep. So yeah, okay. I think that is probably, I'll just scroll to the end. Okay, I think that's probably it. So I'll see if there's any last question, I guess. And it looks like we're good. So want to thank you, Tim, for this. Just on the slide you're seeing basically there, if folks want to contact either Sandrine or me, the emails are there. I'll remind folks the next webinar is on February 5 by Dr. Igor Borstin. And just to ask you, I think you'd indicated before, Dr. Lash, you'd be willing to have this video posted on the HESI website.
Sure.
Okay, okay. I didn't know if, do you have any other questions, Sandrine?
No, but I saw some people requesting some studies. So what we can do is also post some key studies on the website for people who want to learn more about QBA and its utility. There were a few questions about that.
Yep, great. So, okay, thank you. Thank you very much.
Thank you
Dr.
so
Lash.
much,
Have
Tim.
me. Good to
Thanks
see
for
you all.
attending.
Thanks
Okay,
all.
great. Yep, bye-bye.
Bye.